Okay, t-test instead of z-test. There's two main situations I want you to be aware of. One would be if you don't have sigma, if you don't have the population standard deviation, then you really need to use a t-test. And just because you're going to be using the sample standard deviation, there's a correction factor. You really need to use that sample standard deviation S. Also, if you have a small sample size and um, no no really bad data, if you have really bad data, then you really shouldn't do a z-test or a t-test. But small sample size, it all seems to be somewhat lining up normal. That would be a good chance to use a t-test. Second one here, we need to figure out the t-statistic. So this is going to be using that formula right here. It's just like the z-statistic formula we were using, except it has S instead of sigma. So we're going to take the sample mean of 98 minus the mu, the population mean of 100, and that gives us -2. And then on the bottom, we have the sample standard deviation of 3 divided by square root of sample size, which would also give us 3. So we have a 1 on the bottom, so it's just -2 divided by 1. Now for the critical t, we do need to look at table C. And in order to look something up on table C, we need to know, are we doing a one-tail or a two-tailed test here? So we look at the alternative hypothesis and we see this less than. This is a direction. It's either less than or more than, which tells us we are doing a one-sided test. One-sided, we also need our degrees of freedom. So we have 9 sample size, take away 1 to get 8 degrees of freedom. So 8 degrees of freedom, one-sided p-value. Let's go look at that. Okay, so start off down on the bottom. We have a one-sided p at 0.05. So we're going to be in this column right here. We're going up until we hit that sample size, well, the degrees of freedom of 8, one less than our sample size. And we do note that our alternative hypothesis is that our population mean is going to be less than the null hypothesis mean. So really what we're going to be comparing our t-statistic to is this -1.86, where if you draw a normal distribution out, we're putting all that 5% in the left tail. So we're really going to be comparing our t-value of -2 to this -1.86. And in this case, by the way, it doesn't ask you, but you would reject the null because we did get beyond, we got more extreme than this cutoff value. So matched pairs t, there's a couple different times where this would work out. One is when you're testing the same person or individual before and after something, or at some point and then at a later point. So this one right here, E, would be a case of that. We're really asking the same 50 students the questions, but one time early in their college career, one time late in their college career, and then we'll just take the difference of those two. We'll subtract those two numbers to get a single change score for each of these 50 students. Here, this is the other type of situation where you'd have a matched pairs. If you have two sets, two samples, but there's a very clear way to match one in each sample with someone in the other sample. And in this case, if you have 200 married couples, we'd match each person with his or her spouse. It's a very natural way, versus here we also have 100 male EMU, 100 female EMU, but there's not a natural way to say which male EMU student gets matched with which female EMU student. So because there's not that natural matching, we probably wouldn't want to do a matched pairs. So this was revisiting a study from quite some time ago, and it's essentially just setting up a confidence interval. So we need to know a few pieces of information. 654 women. Our sample standard deviation is 7.42, and the sample mean is 26.8. And then you're using this, where's our t? Oh, using this formula right here. I was a little crueler to earlier classes where I made them figure out how to adjust the formulas, but this right here is the t confidence interval. Okay, probably the trickiest part here is the t star. So let's revisit how we could find that. We have a random sample, 654 women, so our degrees of freedom would be 653, and we know we want a 95% confidence interval. Okay, so we go to table C, confidence level is 95%, and we scroll down here, we're not going to find that degrees of freedom of 653 over here, just because the chart doesn't contain that many rows. So we're stuck somewhere between this 100 and 1000. Now ideally you would use technology to get the precise t, critical t here, but since we can't do that, we just choose one of these. And typically if you have to make the choice, you go conservative. In other words, you pretend that your sample is less than what it really is. You move up the chart to the nearest row. So we would take this 1.984 as our critical t in that confidence formula. Okay, here we have what is really a matched pairs test. Okay, and when you click on the link, you're looking for the helium football down at the bottom. So here we have the 16 different trials. We have what it looked like with the normal air, how far it went, and how far with the helium that particular trial went. So do notice that this data point is matched with this one, and this one is matched with this one, the 23 and the 16. We need to get the difference of each of them. So 25 minus 25 gives us 0. 16 minus 23 gives us -7. 25 minus 18 gives us 7, and so on. These are the scores that we're analyzing. We're just pretending that this is our one sample. Technically, we have two different samples here, but because we have a natural way of matching the data, we end up with this column of different scores. How much further the helium went than the air did for that ball. Okay, and so what we need to do is make a couple quick calculations. By the way, if you're doing this, you would want to go to File, make a copy so that you could edit your spreadsheet. We need to get the average of these 16 data points, and we need to get the standard deviation of these same 16 data points. So this would be our x bar, and this would be our lowercase s, our sample standard deviation. To get the t star, and the sample size, by the way, would be 16. The t star is perhaps the trickiest. If you go to table C, going 95% confidence, 15 degrees of freedom, then you would find this 2.131 there. 7, this is a big question, and I do recommend that you try to wrap your head around it. It's a important one, and it shows all the different ways of rejecting a null hypothesis. So we have this basic study of 250 eggs per year in general for all breeds of hens, and I think that's roughly correct. But we're studying a new breed of hens, and we want to see if they're different than average. We're not saying whether we think it's higher or lower than average. We're just saying different. In other words, we're looking two-tailed t-test or two-sided p. We have a random sample of 11. That's our sample size n. 95% confidence. In other words, this is the same as an alpha of 0.05. When would we reject the null? So a few different ways. One is we could look at our t-statistic. So in order to know whether or not to reject, we need to know what our critical t-value is. What's our cutoff? What's our target that we need to get beyond, more extreme than? And so to get our t-star, we're looking at sample size, 11, minus 1 to give us 10. So 10 degrees of freedom, two-sided, 95% confident. So if we look here, two-sided P of 0.05 and two-sided 0.05, we need degrees of freedom 10, so that 2.228 is the cutoff that we're really looking for here. And because we just said different, we don't care if we're below negative 2.228 or if we're above positive 2.228. Either one will reject. So here we got below negative 2.228. Here we got above positive 2.228. So both of those would cause rejection. But notice that this negative 2.21 is not more extreme than negative 2.28. So that's why this one we were not able to reject. We could also look at the p-value. So if our p-value is less than 0.05, that would be good evidence against the null and we would reject. So here we have 0.007, that's less than 0.05, so we reject. Notice this one is not less than 0.05, so we don't reject there. Another thing we could do is take a look at our confidence interval. So if we create a confidence interval for the mean and this null hypothesis mean of 250 is outside our confidence interval, we're saying that that's not really one of our likely possibilities for the population mean, so probably these hens are different than the average hen. So in other words, if the 250 is not in this interval, we reject. And here it is not there. Here, 250 is in between these two numbers, so we're not far enough away to reject. Same thing with this situation. We could finally figure out what a t-statistic is, as in this situation G. So to calculate this, we would need the sample mean, 245, minus population mean. So that would give us -5 on top. And then on the bottom, we have 5 divided by square root of 11. Work that out. You get a t-statistic of -3.32, which is more extreme than that boundary of -2.228. So that would also be a rejection.